So today we will talk about problems from 2 previous days, and for whatever time is left, we will talk about persistent data structures. Okay, so we'll start from Monday's contest. Monday's contest was one of the on-site competitions in Russia from 2015. I like that competition because it has a lot of variety in the problems. There are constructive problems, there are dynamic programming, there's geometry, there are data structures. So we'll start with problem A. We'll go over all problems in order, and I will skip easier problems. So the problems like G, H, or L, I'll skip. B, G, A. Okay, so the first problem, A, coincidentally was probably the hardest problem if I think about it. And it's no wonder since it involves 3D geometry. So in that problem we had a sphere, we had 2 points on the sphere, and the circle, which was forbidden. And we wanted to find the shortest path from one point to another that doesn't go inside the circle. So what is the solution on a 2D plane? Well, if we have 2 points in a circle, the optimal solution is, well, either you go straight ahead to your final destination, right? So in case this segment doesn't intersect with the circle, or you should find 2 tangents, like something like this, then go find the second tangent, then use this circular segment. Okay, sounds bad enough on plane, right? So what do we have to do on a sphere? The answer is it's hard. Well, so what are the good properties of a tangent? Well, it's perpendicular in the point where it touches the circle. So perpendicular here, perpendicular here. And so basically, if we draw the plane, so if we consider the circle as a plane that crosses the sphere, and we'll have another plane like this, those will be perpendicular at that point. Well, if you know now sphere geometry, then you can figure this out. But I'd like to tell you about a more realistic solution that, for example, we used to solve this problem, which is kind of a numerical solution, right? So instead of trying to find tangents on a sphere and checking and finding the length of this circular segment, we will just solve the discrete problem. Let's create a graph. Let's divide this circle into a lot of small points. And let's build a graph. So we're trying to find the shortest distance that goes from point A to point B and doesn't go inside the circle. Well, we'll draw edges between the adjacent points on the circle. And we'll also draw edges from the starting point to some points on the circle, from the ending point to some points on the circle. And the only thing we have to check is, does the line segment cross the circle? So we will draw, for example, this edge. but we will not draw this edge. And now we only have an easier problem. Now we only have one segment on the sphere, and we would like to find, does it cross the circle? Okay, so, and this is similar to how you would do that on a plane. Right, so you have 2 points, for example, this one and this one. Basically, this means that we're finding the tangent by really small approximations. Right? So in reality, our solution will just find the 2 points where this is a valid edge, but the next one is not, and this is approximately a tangent. But the solution is also good because we can just get rid of all the edge cases. So for example, where just going from point A to point B is possible, our solution will find that because we'll try to draw an edge from point A to point B. We'll check if it crosses this line, this line segment, this spherical segment, crosses the circle, and just there is no specific if for that case. So I think this problem is good in a sense that you have to find easier solutions, right? So even if you see, oh my God, it's 3D geometry, nope, not solving that. You can try to find approaches that will work, right? So always try to find solutions that you can implement and think about what you're going to code. Okay, so I've seen that somebody solved that in the upsolving, and I would appreciate your input into this problem discussion. So if you like a solution and you would like to tell everyone about your solution, this is appreciated. So if you'd like to tell your solution for problem A or any other problem in the future, please raise your hand and come up here. Nope? Okay, so that was problem A. The error was 10 to the power of -4, which is low enough. So that we can use this approximation of a circle with a polygon. Okay, so problem B was the easy one. Just use the same dynamic programming as you would count normal balance parentheses sequences, but just add one more transition where you don't put anything into that position. Okay, problem C. Problem C was about cutting a convex polygon into some number of shapes, and we would like to find the number of possible sequences of cuts, not sequences of cuts, but the number of possible ways to cut a polygon such that there are exactly k triangles. So for example, this might be a triangle, this might be a triangle, and that's it. So there are 2 triangles here. Okay, so this is similar to Catalan numbers. since Catalan numbers count triangulations, so for example, if k is equal to n minus 2, the answer is Catalan number c n minus 2. But it's a bit more general problem since we have one new parameter k. Okay, let's see. Let's use dynamic programming. Let's define count n and k. Is a number of ways to cut a polygon with n vertices such that there are k triangles. Okay, so if you remember how does the recurrence relation for Catalan numbers and triangulation works, you remember that we fix some edge. And this edge belongs to some face. Right? So this border edge belongs to some face, for example, this one here. And in general, this picture will look like this. So we have the edge 1, 2. And if we look at the face it belongs to, then it cuts some parts of the outside polygon. So here we have n1 vertices, here we'll have n2 vertices, n3, and so on. So this is how we use values of count n and k for smaller problems, right? So each smaller polygon here is a subproblem that can be solved using the same technique. Here we choose some edge, some borderline edge, and again try to cut this smaller polygon into triangles and non-triangles and so on. Okay, so what do we use here? Okay, so we need some additional dynamic programming to go over all this. So first, we'll count the number of polylines such that here we have x vertices. So we'll have one more dynamic programming, dp. Okay, so x is the number of vertices that we've used so far. So we'll have to use n in total. And the k is the number of triangles that we've created so far. And we need one more parameter to know the lengths of this polyline. So if this only has 3 vertices, then we've created one additional triangle. Right? So if this looks like this, so 1, 2 here, one edge and one edge, and we have 2 subpolygons here and here. This means that we've created a new triangle, and we have to add 1 to this number k. L is the current length of the polyline. So x is the number of vertices. K is the number of triangles. And L is the length of the current polyline. And so the initial condition is dp. We only use 2 vertices. We have 0 triangles so far, and we have 2 vertices in this polyline that contains 1 and 2 is 1. Okay, any questions so far? Okay, now let's calculate. So dp of n, of x, k, and l. Well, let's calculate how many vertices does this part contain. So we would like to calculate how many vertices are in this part. So we add one more edge to this inside polyline, and we'll see how many vertices does this cut. So it's a sum over all y's. Well, there is at least one new vertex. So from 1. And what's the largest amount? Well, our initial condition is x equal to 2. So up to x minus 2, I guess. So we take dp. Oh no, there is one more sum, right? So first we iterate over how many vertices are here. Then we iterate over how many triangles are in this part. So it's k prime from 0 to k. And then we're ready to sum some numbers. So it's dp of... Okay, so we add at least one more. It's x minus y, k minus k prime, and l minus 1, plus, times the number of ways to create such a polygon on y plus 1 vertex, since we use the last vertex and we use y more vertices here. It's count of y plus 1 and k prime. Okay, so let's calculate for now what's the complexity of this solution. Well, the complexity of the solution is, and by the way, in the end, count and k is equal to, well, there are two cases, right? So we add one more triangle using this polyline or not. So in case we don't, it's dp of n, k, and when l is at least 4, plus dp n, k minus 1, and 3. And so we calculate dp array using array count, and we'll calculate count using dp, and this way we can calculate it for all possible n's and k's. Okay. So what's the time complexity here? So here we have n squared states, well, even n cubed for now. So we have n cubed states, and the transition for each state is done in n squared. So the total time is O of n to the 5th. Still too slow for when n is equal to 300. Okay, now let's optimize. So first you can notice that values of L higher than 4 are all the same, higher than 3 even. So 4, 5, 6, we don't care what is the real length of this polyline, as long as it's not 3, as long as it's higher than 3. So we can have L equal to not just all possible numbers, but we'll start L from 2 to 4. So L can only have 3 different values. And here we'll just add the same, but for L. Well, when n is equal to 4. So if L is equal to 4, we'll add the same, but with the parameter L. Okay, now it's n to the 4th. As far as I've heard, this, with some optimizations, might be good enough to squeeze into the time limit, since the constant is pretty low, right? So here you're trying all the numbers, here you're trying all the small numbers. Okay, so one more optimization is, well, this part looks a lot like polynomial multiplication. So here we sum over all possible k prime from 0 to k and multiply something that depends on k prime times the something that depends on the k minus k prime. And we would like to save the result in h of k. Right, so this looks a lot like polynomial multiplication, and in fact that this is a polynomial multiplication. So you can optimize this part with fast Fourier transform to get n cube log. Which is, I think, is good enough already. So if you have a fast Fourier transform implementation, then this is a working solution. But I love generating functions. So there is a solution in big O of n cube that involves generating functions. So instead of calculating this dp, we'll calculate our new dp that does not depend on k. So dp prime of x and L is the sum, and this will depend on some parameter z. And this is the sum of dp x k L times z to the power of k, and will sum over all possible k's. So if you know generating functions, this should be familiar. Well, it turns out that if we calculate this, and again count similar, we define count prime of n of z as sum over all possible k's, count n k times z to the power of k. So basically, we assign a weight to each triangulation equal to z to the power of k, where k is the number of triangles in that way to cut and regular polygon. And we sum over all of this. Well, this is a polynomial, right? So even if I have infinity here, this is a finite sum, and this is a polynomial in Z. So if we calculate the values of this polynomial, then we can use interpolation to get back the results. And turns out these values are easy to calculate. So for example, this sum turns into dp x L, dp prime of x and L of z equal to dp, well, sum over all y's. These formulas might be off by plus or minus 1. Not sure if they're correct, but I think that's the correct idea. So we sum over all y's from 1 to x minus 2, dp prime of x minus y and L minus 1 of z times the count of y plus 1 of z. So basically each time you see this kind of convolution formula, this one, you can optimize it either by using polynomial multiplication, or you can, instead of calculating coefficients of a polynomial, you calculate the values of this polynomial in certain points. So here you can just use z from 0 to, so it's a polynomial of degree at most n minus 2. So we need n minus 1 point. So we use z from 0 to n minus 2. We evaluate this. So this is the only n linear formula. So for a fixed z, well, this has only linear number of states, and the formula is linear for, and the transition can be calculated in linear time. So for fixed z, this is calculated in big O of n squared. So we have to calculate it for n values of z, and then we use interpolation to get the coefficients, which is what we need. So, like, I like generating functions myself a lot. So I love when there is a generating function solution that can be applied to some combinatorics problem. There is a solution that might be easier to explain. So it somehow does different dynamic programming, and it can be solved in n-cube time. I'm not sure I can explain it, so I think there is a team that solved it during the contest with some cubic solution, and if you'd like to come and describe it, I'd be glad to hear it. I think everyone else too. No? Okay. Okay, so problem D might be my favorite problem on centroid decomposition. So in problem D, we had two types of queries. Color, so we had a tree, as usual. We had to take the vertex and color all the vertices that have the distance at most d into color k. So for example, color all the vertices that have distance from this vertex at most 2. So we'll color this subset of vertices. And there is another query, color, for example, vertices that have distance from this vertex at most 2. So we'll color this subset into blue. And the query is return the color of the vertex. Well, this contest was held at times where centroid decomposition was not really popular. So this is where a lot of teams learned about what a centroid decomposition is. And then I think after this, it became really popular. And this is a good demonstration of how centroid decomposition works. So again, we'll use centroid decomposition to answer these queries. So we have a centroid of the tree, and we make it a root of the corresponding tree. Then we remove this root and build and find centroid in each of these subtrees. So here, basically recursively we'll find centroids in each subtree, and so on. So a centroid is a vertex. It's a unique vertex, or there are two of them, such that all the subtree sizes are at most n divided by 2. Because then, if we remove this centroid, the size of each tree is at most half of what it was before. And that means that there will be logarithm of stages of this process. So we have a forest, find a centroid in each tree, delete it until we removed every vertex. So there will be at most log n, log base 2 of n, round it up, round it down even, phases. Okay, so it can be a specific topic on how do you implement centroid decomposition, or what do you do with centroids at all. But for now, what I want from my centroid decomposition is I'll have some data structure for each centroid. And for every vertex, I will store the list of centroids. So each vertex, every vertex was removed at some point, right? So in the first phase, it had some centroid, and it was the subtree in the subtree of that centroid on the first phase. Then on the second phase, it was in the subtree of some another centroid, and so on until it was the centroid. Then it got removed. List of centroids for each vertex. So that will be enough to solve this problem. Okay, so now how do we execute a query? So first of all, let's color. So we have this vertex. Let's go over all centroids, and instead of coloring, this is a hard query, you know? Querying all the vertices that have distance at most d is pretty hard. They have some pretty complicated structure, and you cannot do that if you just root a tree at some vertex and you hope to solve something in logarithmic time. That's probably not happening. And usually, when you have this kind of queries, so do something with all vertices at distance at most d, or at most 2, 3, 4, and so on, usually it's a good hint that you'll have to use centroid decomposition for that. Because these queries can be easily translated into this. So for each vertex, we know the list of its centroids. So we know that we have to color all distant. We have to color all vertices at distance at most d from that vertex. Well, instead, let's color. Suppose this distance is equal to t. So the distance from this vertex to the first centroid is t. We can pre-calculate that while we build our centroid decomposition. So for each vertex, we would not just store the list of centroids to that vertex, for that vertex, but we will also store the distance to the centroid. So a pair, for each vertex we have a list of pairs, a centroid and the distance to the first centroid, the second centroid and the distance to that one. So we'll say that if there is a query color C, distance D, we will transform it to this subtree query, which means color all vertices that have distance at most D minus T into color C. So for the first centroid, I'll add the query, color all the vertices that have distance at most D minus T to the root into color C. So I will do the same for the second centroid. So here we have some other distance, D prime, and there will be another query, color all the vertices that have distance to this centroid at most D minus T prime into color C. And so on. So we'll create a separate query for each centroid. We'll store those queries somehow. So now each centroid has a list of queries. So first of all, well, the first centroid has all the queries. Well, maybe not all the queries, since this might become negative. In this case, we don't do this query at all. So D1, C1. So the first query was color all the vertices that have distance to that centroid at most D1 into color C1. Then all the vertices have distance at most D2 into color C2, and so on. And these are sorted by time. So this was the first query. This might override it, so that we don't even need the first query, and so on. So which queries are useless? So if we have some query DI, CI, and we have some later query DJ, CJ, and the distance for the former query is greater than DI, so DJ, if DJ is greater than DI, this means that we completely overwritten all the results of this query. So we colored all the vertices on distance up to distance 100, and then after some time we colored all the vertices that have distance at most 200. This means that we don't need this query. So this means that we can use a stack. So if there is a query, the first query that has smaller distance than some former query, then we don't need the first one. This means that we only need queries that we go forward in time, but that have smaller and smaller distances. So we can view this as a stack. So we have some very old query that had very large distance. Then we have some smaller query that had a little bit smaller distance, but it has overwritten all these vertices. But this the first query is still relevant since there might be vertex at some distance like this, and the first query will still be relevant. So we have some decreasing. So whenever we add the query to the centroid, something like this, we have to pop from the stack all the queries that have smaller distance. So we remove this one, and now we have another stack. Okay. So, and we'll do that for every centroid. We don't do that if this distance is smaller. Well, why does this cover all the vertices that we can? Well, this will cover every vertex, since for every 2 vertices, there is a centroid for every u and v. Every 2 vertices have a common centroid. Is a common centroid. Well, let's look at the first time these 2 vertices, either one of these 2 vertices was removed, or these 2 vertices were separated. So this means that they are in the different subtrees of the centroid. Maybe there are other subtrees. Well, at the first time, if we look at the first time these two vertices become disconnected, or one of them gets removed, there is a common centroid. Because this means that if we remove this vertex, these two become separated, this means that this is a common centroid. So, and the important fact here is U and V are in different subtrees. U and V are in different subtrees. So if this is U, this is V, this is C, different subtrees. And the distance between those 2 vertices can be calculated. So the distance from U to V. If these are in different subtrees, then the distance from U to V is the same as the distance from U to C, then from C to V. This means that when, for example, if we have a coloring query at vertex U, then we'll add the query to this centroid, and if this vertex was affected, then it will be affected by this query at this centroid, and if this vertex was not affected, then this query will be just too high. So this is an important fact about the centroid decomposition, that every 2 vertices have a common centroid, and the distance between those 2 vertices can be calculated as distance to that common centroid plus the distance, well, the distance from the first vertex to the common centroid plus the distance from the second one. This is, by the way, this is a way to not use LCA and calculate distances between every pair of vertices in log n time. You can build centroid decomposition. You can pre-calculate distance from every vertex to its centroid. Then, to find the distance between 2 different vertices, you have to find their common centroid and then take the sum of 2 distances. You don't need to use LCA, but it's probably more convenient to use LCA. Okay, now we've done with the query. It works in O, big O of log n amortized. Because we add the query to each centroid. And then we remove some, but each query is added once and then removed once. So even though one query might remove a lot of queries from each stack, the total time will be still log n times the number of queries of this type. And how do we answer the query? Well, we need to find the latest query. So for example, if we have a distance somewhere here, so distance grows here, time grows here. And we need to find the latest query that covers our vertex. And we'll need to do that for each centroid. So we'll just binary search on this stack. Binary search on each stack. So there are log n centroids, and binary search takes log n for each centroid. So the total time for the second query is big O of log squared n. But the cost is really low. So these are really fast operations, right? So binary search on a stack is very fast, and usually the size of each stack will not be linear for all possible centroids, and usually the the number of centroids is not log n most of the time, and so on. So the total time is n, well, I'll denote n as the number of queries and the number of vertices, so it's n log squared n. Yes? Avoiding what? So, so suppose we have a problem, right? So we need to calculate the distances between some pairs of vertices, right? Hmm?
Not using LK.
So yes. So assume that you have a problem where you need to calculate distances. You just have some queries and you need to calculate distances between some pairs of vertices. The common solution for that is use LCA, find the lowest common ancestor, and just find the distance to that, to the LCA from the first vertex and the second vertex. Well, you can, if you dislike LCA for some reason, then you can build a centroid decomposition. You have two vertices, you can find their common centroid and take the sum of distance from the first vertex to that centroid and from the second vertex to that centroid, and that will be the real distance between these two vertices. Okay, so because if this is a common centroid, this means that U and V are in different subtrees, and the distance between them, well, and the path from U to V passes through C, necessarily. So the distance between U and V is just distance between U and C plus the distance between C and V. Okay, any more questions? Okay, let's go to problem E. Problem E was a geometry problem, and yes? Sorry? No, they have exactly one centroid in common. Well, and this is a centroid. That centroid is a vertex that gets deleted when these two vertices become separated. So vertices U and V. So if there are, so let's look at the first centroid, right? So if they are in the same, well, yes, this is a common centroid, but like we need to find the latest common centroid. Wait, yes, that's correct. Yes, sorry. So we need to find the latest moment where two vertices become separated, and this is basically the latest common centroid. So centroids for two vertices are the same up to some point, and then they become different, or maybe one of the vertices becomes deleted, and we need to look at the latest one. Yes, that's correct. Sorry. So we need to find a moment where u and v are in the different subtrees of that centroid, and that should be the latest one. Yes, so we just go from left to right, compare centroids, and we find the latest one where two centroids are the same. Well, in this problem, we don't need to do that explicitly. This was just for proof that our reduction to this subtree queries is correct. But in some problems, you do need to find the common centroid. Okay, problem C was a geometry problem. And we needed to cover a set of points with a rectangle that was not necessarily axis aligned. So something like this. Not the best rectangle in my life. And good enough. So the usual solution for this kind of problem is to build a convex hull, and since the rectangle is a convex figure, then if it contains the convex hull, it contains all the others, and it must contain the convex hull. So now the problem is we have a convex polygon, and we need to cover it with a rectangle. Well, it turns out that one edge of the convex hull will always be parallel to some side of the rectangle. Some side of the rectangle is parallel to the side of convex hull. Okay, so this means that we can try all possible sides, and we can assume that, okay, so our rectangle is parallel to this side. Then how do we calculate the smallest rectangle that contains our convex hull, and where this is one of the sides of the polygon, of the rectangle, sorry. So this is the same as we have this line, and we need to find the farthest point in that direction. We have to find the farthest point in the opposite direction, and we have to find the farthest point in the perpendicular direction. So if we know all these points, so we know this one, this one, this one, and we have these two as a side, then we can build our rectangle. Right? So how do we build it? Well, we know this vector. We can build a perpendicular vector. We can build a line through this point, where either this is the normal vector or this is the vector of the line. We can do the same with this point. So we find the farthest point in that direction and in the opposite direction. We build the line through that point with this supporting vector, and we build the parallel line that passes through this point. So if you have a point and the vector, how do we build a line? So a line is usually I usually use lines as an equation. Ax plus by plus c is 0. So the only thing I need is to figure out how do this a, b, and c look like. Well, the line is, I like to look at a line as the follows. So there is some point P and the normal vector n, and the line is all such points A such that PA is perpendicular to n. So I like to look at the line as a geometric place of all points where points A, where PA is perpendicular to n. And perpendicular means that the scalar product is 0, and this means that AX minus PX times NX plus AY minus PY times NY is 0, and that's how we get the line equation, right? So it's AX times NX, this is A, plus AY times NY, this is B, minus NX PX plus NY PY, this is C. So basically AB is a normal vector to the line. In case you didn't know that this is a convenient knowledge. So now we know that if we would like to use if we know the normal vector and the point, we can build the line equation. And if we know the vector that should be parallel to the line, we can build the normal vector. So for example, if this is AB, then we can easily rotate the vector by 80 degrees counterclockwise. Counterclockwise is usually the better direction to use in geometry problems. So this vector is minus B and A. Yes? Yes. So we can easily rotate the vector by 80 degrees, and then we can intersect this for 4 lines. So we have 2 parallel lines, and we have 2 parallel lines, and then we can intersect all of them to get 4 points of a rectangle. So this is a solution in big O of n squared. Then we try all possible sides, then we find the farthest point in this direction, in the opposite direction, and in perpendicular direction, and we just intersect 4 lines. Now, we can make a linear solution out of this, and this is somewhat similar to rotating calipers technique. Or like a geometry version of 2 pointers. But instead of 2 pointers, we'll have 4 of them. So we'll iterate over all possible sides. We'll find the farthest point here, here, and here for the first side. And the claim is, if we go to the second side, so if we move to this one, so this point will only move counterclockwise, this point will only move counterclockwise, and this point will only move counterclockwise. And this is very easy to implement. So for example, if we initialize like farthest positive direction, farthest in negative direction, and farthest in farthest positive, farthest negative, and farthest perpendicular. So we just iterate over all possible sides from 0 to n minus 1. Now we're working with pi and pi plus 1. Here's the current side. And then we would like to increase f plus until while the distance to, while the next point is farther in that direction than the current one, we move this f plus. So while, and the farthest point in some direction can be characterized as the scalar product with this vector is the largest. So while scalar product, I'll just say this. So while p f plus plus 1 pi plus 1 minus pi. So this is the scalar product, or I can say it like this, is greater than what's here, what we have at current f plus, then we increase f plus. So we can just use this while loop. While the next point is better than the current one, we increase the pointer. So we do this with the perpendicular, but instead of scalar product, we use the vector product. And with f minus, it's a little bit difficult since we need to initialize it correctly. So, for example, we can find the farthest point in the opposite direction in the beginning, and after that it will move as all other points, but here we'll have less sign instead of greater one, and so on. So even if you don't know how to prove that the side of the that one side of the rectangle will be parallel to the side of the convex hull, then you can just guess it. It's usually true. And even if it's not, like if you have a solution and you got wrong answer, the common might be a bad advice, but the common technique here will be to, well, let's assume that the function between two adjacent angles is good enough. So, well, this might not be the optimal rectangle, and this might not be an optimal rectangle. Well, maybe something in between is an optimal rectangle. So we can choose, basically we can build all the different events. So for example, the side is now parallel, one side of the polygon is now parallel to this side, or one side of the polygon is now parallel to this side, or this is now the farthest point from this rectangle. You can build all such events, sort them, and use ternary search between the adjacent events. So this is usually the way to go. So if you assume that the function that you are trying to optimize is good enough, so doesn't have any weird local minima, then you can just use ternary search between two adjacent events, and it's probably good enough. So you build all these events where the function you are trying to optimize is smooth, so it doesn't have any weird breaks. So for example, all four points that are on each side of the rectangle do not change. So for example, if we fix these 4 points, we have some range of angles where these 4 points are on the side of the polygon, on each side of the rectangle. So if we fix the angle of one side. So if we fix the direction of one side, then we can easily find these 4 points. We can easily calculate the area and find the minimum one with the ternary search. In this problem, this is true. I don't know the exact proof of it. There is an article somewhere. But this is true. Okay. This was problem E. So it's been an hour. Should I talk faster or should I go into less details, or is it fine? Okay, it's fine. Problem F. Problem F was about sums, and there were 2 parts in this problem. The first part was to realize that the number of ways to represent a number as a beautiful sum is number of ways is the same as the number of odd divisors. And the second, find the smallest number with that number of odd divisors. Well, first of all, why is the first thing true? Well, what is the formula for arithmetic progression? This means that n is if n a plus b, its average times the number of numbers. So it's a plus b divided by 2 times b minus a plus 1. And it's the same as 2 times n equal to a plus b times b minus a plus 1. Well, you see that the right side is a product of 2 integers with different parity. So one of them must be odd and one of them must be even. This means that all the 2's in factorization of 2 times n are in either a plus b or b minus a plus 1. This means that we can uniquely choose an odd divisor to be one of these parts, and then the other part is all the 2's along with all this stuff. So the number of ways to represent the number as a beautiful sum is the number of odd divisors. So now for the second part. The second part, well, if we know that if we know the factorization of n, so it's, first of all, we don't need any 2's, right? So since we only consider the number of odd divisors, if we remove all 2's from the factorization of n, the answer is still the same. So we don't need 2's in the smallest number. So this is 3 to the power of k1, 5 to the power of k2, 7 to the power of k3, 11, k4, and so on. And the number of divisors is k1 plus 1 times k2 plus 1, and so on. So, since the number of divisors only depends on these exponents, it makes sense that this should be a decreasing sequence. So k1 greater than or equal than k2, k3, and so on. And ki plus 1, well, this should be equal to, well, this should be n, right? So let's denote this by some n large, and this is n. which is the number of divisors that we would like to get. Okay, so now the problem is as follows. So we need to find a decreasing sequence of integers such that k1 plus 1 times k2 plus 1 times and so on. The product is equal to n. Well, this can be done with a simple brute force search. So we can write a recursive function where we have our last k, the position that we're at, so the current index, and the current product. Well, let's not store the current product, but instead store the product that we still need to get. Remaining product. So now we need to try all possible divisors of this remaining product, and for I divides remaining product, and I is less than or equal to last k, we need to do a recursive search at last k at I was the last k used, then index plus 1, and the remaining product is divided by I plus 1. So I plus 1, where I plus 1 divides the remaining product, sorry. So this way we can try all possible numbers that can be candidates to be the optimal number with the odd number of divisors. And now the only thing we need to do is to find the minimum one. And it's pretty hard since these are large integers. So for example, when n minus 1 is prime, when n is prime, so when n is prime, the answer is 3 to the power of n minus 1. And this is a very large number since n is up to, well, not too large, but large enough that you cannot easily handle it in your program. So what do we do when we need to compare two large numbers? Well, these are pretty special numbers, right? So we know numbers k1, k2, k3, k4, and so on. Well, turns out that we need to take logarithms. We can take logarithms and compare logarithms instead of actual numbers. And it's really unlikely that two numbers that have the same number of divisors will be really close. And they're both candidates to be the answer. So we need to take sum of log pi times ki and compare those. So instead of comparing actual numbers, we'll compare logarithms. And we need to calculate the minimum number modulo 10 to the power of 9 plus 9 that we can also do in this recursive search. Okay, so this is the problem. Two steps. First one is realizing what does the answer look like, and the second one we're finding the smallest number there is by just a brute force. And usually this kind of brute force works really fast. So whenever you're trying to find all possible decreasing sequence of exponents, usually there's not too many numbers that satisfy this. And of course, to optimize this, you need to pre-calculate all the divisors of n. So you don't factorize n at each recursive call, but instead you just run over all possible divisors there are. Okay, any questions? Okay, so I'll skip problems G and H, since most of you solved them. Problem I. Okay, thank you. Yeah. Problem I was an easier one. Problem I was a problem on combinatorics, and we were asked to represent n is a sum of binomial coefficients, c x1 by 1 plus c x2 by 2, the xk choose k, where where those x's are increasing. Okay, turns out that the greedy strategy works. So we'll reconstruct the number from the largest term to the smallest term. First of all, we know the k, so we'll choose the largest sk, xk, choose maximum xk such that xk choose k is less than or equal to n. Then I choose maximum xk minus 1 such that xk minus 1 choose k minus 1 plus xk k is less than or equal to n, and so on. So why does this work? Well, the only thing we have to check is xk minus 1 is less than xk. And it turns out that this representation will be unique, since x1 choose 1 is just equal to x1. So we can represent any integer using this algorithm. So in the end, we will always choose the correct one. And the only thing we have to prove is that the next number that we'll choose will be less than the number that we chose on the previous iteration. So why is that? So let's take the corner case. Let's assume that this is not true. Xk minus 1 is greater than or equal to xk. So this means that xk minus 1 choose k minus 1 plus xk choose k is less than or equal to n. So this is greater than or equal, since binomial coefficient is an increasing function of xk, so this is greater than or equal to xk minus 1 xk choose k minus 1. Let's do it like this. And this is equal to strictly greater. It's equal to xk plus 1 choose k. So, and this is greater than n. So each term, each xk that we choose on the next iteration cannot be greater than the previous xk, because suppose that xk minus 1 is greater than or equal to xk, then this means that this sum is less than or equal to n. But this term, if we replace xk minus 1 by xk, this means that we made the number smaller, since if we increase the number in binomial coefficient, then the value is increased. So this is greater than xk choose k minus 1. And since the sum of these two is the fundamental property of binomial coefficients, is xk plus 1 choose k. But this one is greater than n, because we chose xk in such a way that xk choose k is less than or equal to n, but xk plus 1 choose k is greater than n. So we chose the maximum k. So we chose the unique k, xk, that has this property, and but there is a contradiction. So this means that we can choose greedily each time, and the only thing that's left is the implementation, right? So there are a couple of corner cases. So for example, when k is equal to 1, you choose x1 is equal to n. When k is equal to 2, it was kind of a special case in our solution when we solved this contest, because you cannot just increase values of xk greedily, since the maximum k will be about 2 times 10 to the power of 8, which is kind of dangerous. So in this case, you can use, for example, binary search, since the formula for the second binomial coefficient is easy enough. And when k is greater than 3, you can just find the maximum xk greedily. So you just find the maximum, find the maximum, find the maximum, since all xk's will be less than 1 million. Because 1 million choose 3 is greater than 10 to the power of 16, which was the upper bound in this problem. Okay, so any questions? So this is the greedy problem with binomial coefficients that just take the maximum xk and you can prove that it's correct. Okay, problem J. Problem J was a number theory problem, and we were asked to calculate n choose k. Is n factorial divided by k factorial, n minus k factorial, mod m. N and k might be large, but m is small. Okay, so what usually happens in number theory problems when you have a small modulo is that you want to factorize it and solve modulo prime power. So if m is p1 alpha 1, p2 alpha 2, and so on, you would like to find n choose k mod P1 alpha 1, then P2 alpha 2. Then you can solve it using Chinese remainder theorem. So you can take all these results, and with the help of CRT, you can get n choose k modulo m. Okay, now the problem is how do I calculate n choose k modulo a prime power mod p to the alpha. Okay, I didn't write this formula just so there is a formula, and this will be helpful. So I'd like to calculate n factorial divided by k factorial n minus k factorial mod p to the alpha. Okay, so I need to solve this problem, and to do that, first I will try to represent n factorial as p to the power of t times z, where t is max. So basically, n factorial is a collection of different factors. All the factors that are equal to p are here, and all the factors that are not equal to p are here. So z is not divisible by p. So I collected all the factors that are equal to p here, and all the factors that are not equal to p here. Now, my problem will be to find n factorial divided by p to the power of t mod p to the alpha. So basically, I throw away all the factors of p. I throw away 1p, 2p, 3p, p squared from this n factorial, and I would like to find the value of this product modulo p to the alpha. Well, let's see what does n factorial without all the prime factors p is equal to. Well, n factorial is 1 times 2 times 3 up to p minus 1. Then instead of p, we'll just write 1. Right, so we divided by p. We want to remove all the factors that are divisible by p. So instead of p, we'll have 1 here. Times 2 times p plus 1 times p plus 2 times 2p minus 1 times 2. So there was 2p before, but we can remove it. So, and this is cyclical, right? So this, whenever we reach p to the alpha plus 1, this is the same as 1. Since we're going to calculate it mod it's p to the power of alpha, this is 1 again. So this is cyclical. Okay. By the way, do you know how to calculate this t? So what is the largest, what is the exponent of t in factorization of n factorial? So it turns out that t here is equal to n divided by t. So n divided by p, sorry. So this is the number of, this is the total number of numbers that are divisible by p once. At least once, sorry. Plus n divided by p squared. So this is the total number of numbers that are divisible by p squared, or maybe by p cubed, p to the power of 4, and so on. So this is this infinite sum rounded down is t. Okay, so this is cyclical, and well, let's calculate everything except this. Let's call it f of n. So f of n will be equal to 1 times 2 times 3 times p minus 1, p plus 1 times 2 times p plus 2, sorry, plus 2, 2p minus 1, and so on up to n. And we take all of this mod p to the power of alpha And now we have to deal with 1 times 2 times 3 times 4 and so on. Well, turns out this is just f of n divided by p. So this is the same factorial. So on all these cancelled places, on all these places that contain p as a factor, now we get the same factorial that we needed to calculate. Rounded down. And this can be calculated easily because even if n is large, p to the power of alpha is small. So this product is a product of some number of chunks that are the same plus some tail. So we would like to calculate it modulo p to the power of alpha, which is small, and then we can do this. So this formula can be, so f of n can be calculated. In big O of p to the power of alpha times log n base p, which is small enough, right? So we have 1 million, so this is at most 1 million times log, good enough. So if this is 1 million, then this is probably small, and so on. Okay, so now we can represent n factorial as p to the t times z. So now we know that n factorial is p to the t times z, and we only know z mod p to the power of alpha. Well, now we need to cancel those out, right? So n factorial. So if n factorial is equal to p to the t times z, z1, t1, z1, k factorial is p to the power of t2 times z2, n minus k factorial. So we just call the same function 3 times. We get this values t1, z1, t2, z2, and t3, z3. And thus the final answer is n factorial divided by k factorial n minus k factorial is z1 divided by z2, z3 times p to the power of t1 minus t2 minus t3, and all of that is taken mod p to the power of alpha. So this is the final result. This is how you calculate n choose k modulo prime power, and then you can solve Chinese remainder theorem modulo all prime powers in factorization of m to get the final result. By the way, here you don't need the fastest algorithm to solve Chinese remainder theorem. Here you can just say that whenever you have a system like this, so some result is A1 mode M1 and X is equal to A2 mode M2. So whenever you have this kind of system, you can solve it in big O of min of M1 and M2. So you don't need any fancy algorithms. You don't need extended Euclid here to solve the Chinese remainder theorem. You can just try all possible values of the smaller modula, because x, well, let m1 be less than m2. So we know from the first one that x is a1 plus some t times m2. And we can try all possible values of t from 0 to M1. Just check. We know that the first equation is already true if we try the values of this form. And now we only need to check if the second one is true. Okay, have I messed up? Is it the other way around? One minus one. But yeah, it should be the other way around, right? So we use A2 plus, no, TM2, and then we try all possible T's. Yeah, this should be right. And then we check if the first equation, if the smaller equation is true. Okay, so this was the number theory problem, and I think this trick with calculating n factorial mod prime number or mod prime power is, I've seen that at least a couple of times, so I think that's an important trick to know. So this is how you calculate n factorial mod p, and you can also collect all the prime factors of the power of p in the n factorial using that formula. Okay, any questions? So I'll skip problem L, and there is problem K. Should I skip problem L? Yeah. So problem K was one of the ad hoc problems. So since you need to come up with an original solution for that problem, there is no like standard algorithm to solve those. Okay, so let's see what happens for small values of n. So what if there's just one person? So suppose k is large, so the number of oranges that we need to define is large enough. So what if n is equal to 1? What is the result? What's the minimum number and the maximum number? Well, the minimum number and the maximum number is, of course, k, right? So just k. Since there is only one person, it takes all the oranges himself. So when n is equal to 2, we know that the first player can just take all the oranges, and second one cannot do anything. So this is the minimum and the maximum result for the first one, and this is the minimum and the maximum result for the second one. Almost in all cases, the minimum and the maximum is the same except for one. Sometimes one person can receive either 0 or 1, and these two cases can happen. So when n is equal to 3, now the interesting thing becomes, well, can the first player guarantee, can the first player take all the oranges himself? Why not? Yes, so if it's like this, then the second player will always vote no, because in case he loses, he knows that he can guarantee K to himself. So the second player always votes no. So we just don't bother giving any oranges to that player. And the second is always 0. But the third one, well, if we give him 0, then he knows that when n is equal to 2, he gets 0 anyway. So he will vote against. So to make sure he doesn't vote against, we have to give him 1. So it's k minus 1, 0, and 1. So if we have 3 players, the first one can guarantee k minus 1, the second one gets 0, and the last one gets 1. What if n is equal to 4? Well, the same, but shifted, right? So the first one gets k minus 1, second one gets 0, this one gets 1, the last one gets 0. Okay, so basically we need to make sure this one gets something. So this one always votes against us, doesn't matter. So we need to make sure this one votes for us. Because in the next case he gets 0, so it's optimal for this player to vote against. And so on. So you can notice the pattern. K minus 2, 0, 1, 0, 1. So we take all of them ourselves, and then half of the oranges we need to divide among those. Well, this only happens when k is large enough. So if k is large enough to make this process for all possible n's, then it's fine, right? So this happens if n times 2 plus 1 is less than or equal to k, I think. Okay, so what if k is not large enough? So during this process, at some point, the first player will have 0. And to not be negative, since if we're eliminated, it is considered that we get negative oranges. So we'd rather get 0 oranges than negative 1. So we'll need to distribute some oranges that we have among those that disagree. So if n is odd, then we give 0 to ourselves, and then give oranges to someone else. So it's 0, 0. And it's odd. And if n is even, then we need to give oranges to some 0s too. So we have some 1s that we can bribe, basically. And there are some 0s. And it doesn't matter what subset of 0s do we give oranges to, so that they agree. So here is the only case where we can output 0, 1. So some 0s here can get oranges and some cannot. So in some cases they will get 0, in some cases they will get 1. So think that's it for my problem. I might not understand the solution myself well enough to tell you, but I hope this is a good enough start to, well, for this problem, you can implement the brute force, not brute force, but some kind of dynamic programming solution for small n's and small k's. And you know what is the distribution for small k's. You can derive the rules of how they look for larger k's, and then you just implement this kind of solution. So there are two major cases, so when k is large and when k is not. And what happens when k is small is a little complicated. Okay, so we're done with Monday's contest. This took us almost 2 hours. A little longer than I expected. So after an 8-minute break, we'll discuss flow problems. Don't think we're going to discuss persistent data structures today. So this will be tomorrow, not tomorrow, but tomorrow we'll have a free day. Tomorrow I have a free day, you have a sponsor day. And so today, after lunch, we have a normal contest. So one of the Russian, please don't get offended by today we have a Russian competition for school students. This is the hardest one that you can imagine. So not all professional ICPC teams can solve all problems on that contest. And yeah. So 8-minute break and come back here to discuss flows. Continue with the flows. There are fewer problems on flows, and I'll skip the introductory ones. So I'll skip A and B, since A and B are just to implement the max flow algorithm or find the minimum cut using the max flow. And I'll start with problem C. So in problem C, we had to find, basically we had to build some wall, so there is no grid path from one vertex to another. So there is some grid, there is A, then there is B, there are some mountains impossible, there are some places where you cannot build walls. And then you had to build something so there is no path from A to B. Okay, so this can be formulated as a min cut problem. So we basically want to remove some edges in the graph such that there is no path from A to B. And this is our grid graph. But here we remove vertices instead of edges, right? So basically some are already removed. Mountains, you can view mountains as we can remove them for 0 cost. And normal cells, we can remove them for cost 1. And the minus cells, we can remove them for cost infinity. So we cannot remove them at all. So now we have the formulation. We have a graph. Delete some vertices. So there is no path from A to B. Well, First, let's delete edges. So, not vertices, but edges. Well, turns out it's just run the min cut. So we have the graph, we have the vertex A, we have the vertex B, and we have some edges, undirected ones in this case, but doesn't matter. And each edge has a cost, and this is basically min cut, right? So we want to find the separation of the set of vertices into two sets, such that the cost of all edges from the first part to the second part is minimized. So what do we do if we want to remove vertices instead of edges? This is a common trick in max flow problems. What we'll do is, instead of one vertex with some incoming edges and some outgoing edges, we transform it into two copies of one vertex. So we have a copy for all incoming edges, so all edges that go into that vertex. Then we have a copy for all outgoing edges. And then we add an edge with Ci, where Ci is the cost to remove this vertex. And all of these edges should be infinite, right? So we cannot remove edges now, but what we can do is remove vertices. And removing vertices corresponds to basically cutting this edge. So we need to cut some vertices into two parts, such that there is no path from A to B. So now the solution is as follows. So for all mountains, there is no such edge, or we can make an edge with cost 0, but this doesn't do anything for our max flow algorithm. So for normal cells, this will have cost 1, and for mountains, this is 0, and for minuses, this is infinite. So we cannot cut this edge if we cannot build a wall here. So how do we restore the answer? Well, we will look at all these vertices that have this edge, for which this edge is saturated. This will mean that we have a cut. This edge crosses cut, and that means that we should remove this vertex or put a wall segment inside this vertex. And if the maximum flow is infinite, so if it's larger than n times m, so if it cuts through any infinite edge, this means there is no way to build walls such that there is no path from A to B. So for example, in the last sample, this is just A infinite edge B. And of course the max flow is very large. Well, of course, instead of infinities, you will use some large values, like 1 billion. So if you see, if the max flow is larger than n times m, for example, then there's no solution. Okay, the next problem. Any questions about this one? So this is a very common trick to split vertex into two parts, and all the incoming edges go into the first part, all the outgoing edges go from the second part, and there is an edge that corresponds to cutting this vertex in two. Basically removing this vertex from the graph. Okay, problem D was about monotone Boolean functions. Okay, so what is a monotone Boolean function? Well, if we draw a graph or a hypercube, so for example, 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0. It is similar to the closure problem, right? So we need to choose some subset of these vertices to have value 0, and some subset of these vertices to have value 1, such that there is no edge. No edge 1, 0. Right? So we want to mark some vertices as zeros, mark some vertices as ones, such that there is no edge from 1 to 0. This is enough to make this Boolean function monotone. Okay, but some vectors are already defined, and some have no value at all, so we can define them any way we want. So the problem is to divide all these vertices into two parts is similar to the minimum cut problem. So dividing into two parts is pretty much min cut. Well, dividing into two parts is cut, and now we want to minimize the cost of dividing into these two subsets, which is why we want to minimize. So now we think about how to formulate this problem as a min cut problem. Okay, so some vertices already have some values, some don't. Okay, so I drew this graph here. How many edges does this graph have? Well, this graph has at most 2 to the power of n times n edges. To be precise, I think it has 2 to the power of n minus 1 times n edges. Yes. So, by the way, this is an improvement from, so it's not 3 to the power of n edges. Right, so we only draw edges from one binary vector to all binary vectors where we replace 0 by 1. We don't use all possible ways to replace zeros by ones. We only replace 1, 0 into, we only make 1, 0 into 1. So that's why there are 2 to the power of n minus 1 times n edges and not 3 to the power of n. Okay, so let's make all these edges infinite. Right? So we don't want to have an edge from 1 to 0. This is why in min cut S and T, this will correspond to f of x to be 0. And this will correspond to all binary vectors where f of x is 1. And we don't want an... Should be the other way around, right? 1 and 0. And we don't want an edge from... We don't want an infinite edge from S to T. That's why we're constructing it this way. Okay, so we'll have an artificial source and artificial sink. Now, for each vertex, we will draw an edge to either S or T, or maybe none of them. And we will find what is the cost of changing that vertex. So what is the, so if this, for example, f of 3 zeros is defined to be 0, if we want to change, if we want it to be in the first set S, this means that it should be reachable from S. And if it will be on the second set T, then we need, basically we need to create such an edge. So including it in set S will cost 0, and including it in set T will cost 1. Okay? So if f of 3 zeros is 0, is defined and is equal to 0, what kind of edge we need to create? So we either need to create this kind of edge, or with capacity 1, with cost 1, or this kind of edge with cost 1. Which one should we do? Yes?
In the column, the values of the function are already defined.
Yes.
We want to redefine.
Yes, for some inputs, they are defined, and for some there is.
All inputs are defined, and we want to redefine it.
Yes. So if this is already 0, the cost to redefine it to 0 is 0, and there is a cost 1 to make it 1. Okay, so if it is included, so basically the cost included into set T is 0, and the cost to include it into set 1 is 1. Yes?
I think what he meant is in the input we have like some binary.
Yes, and here I don't have all the values defined.
All binary vectors there, and the difference is for some of those that are not in the input, you can choose either 0 or 1 and between off, right?
Yes, yes. Okay.
Because you say that some vectors are defined and some are not.
Yes, some are defined, and some are not. So the ones that are
What I understand is that all vectors have the value defined and we want to redefine it.
yes, but in the input we have only some of the binary vectors that have the defined value. So you can see that the first line has 2 inputs, right? N and k. So n might be less than 2 to the power of k, for example. So in some cases, not all of the inputs are defined, and we can define them any way we want. And we want to minimize the number of redefines. Okay, I think I'll change this network a little bit so that S corresponds to 0 and T corresponds to 1. This should be easier to reason with. And to do that, so we don't need to, so there should be no edge from 0 to 1. And so I just reverse, sorry, there should be no edge from 1 to 0. Right, so there should be no pair of binary vectors such that the first one is dominated by the second one, the smaller is 1, and the latter is 0. So I'll draw the edges back. And all of those are infinite. Okay, so now the first set, all those binary vectors that are reachable from S should have value 0, and all those vectors that are reachable from T should have value 1. Okay, so if the value is already 0, then we draw an edge from S to that value with capacity 0. And so for example, this one, there is also an edge from here to here with capacity 1. And if some binary vector has defined value 1, we'll draw an edge to the sink. So after we find the min cut, so there is S, there are some binary vectors that are chosen to have value 0, and there are some binary vectors that are chosen to have value 1. Let's look at the cost of this cut. So the cost of this cut will be the number of these edges and the number of these edges, plus the number of these edges. So these are vertices that initially had value 1, but now we assign them to 0. And these are values that initially had value 0 because we drew an edge from S to that vertex, but now have value 1. So we redefine all those vertices where there is an edge from S to that vertex, but that vertex is in the right part. And we redefine all those inputs where there is an edge from that vertex to sink, but the vertex is in the left part. So all the edges that cross the cut are only these ones. There are some infinite edges, but they don't cross the cut. They only go inside the cut, inside the left part, or inside the right part, or go from right to left, but not from left to right. Since in that case, the cost of this cut will be infinite. Okay? So this is a specific network, and we draw some edges that that help us define what the cost to redefine some input is. So if the value was 0, then we draw an edge from S to that vertex. So if that vertex now, after we find the minimum cut, moves to the right part, we pay the cost for that edge. Okay? So that was problem D. Problem E was an easier one. So basically, here we have some jobs. So there are some jobs. Each job will give us some amount of money if we complete it. And to complete the job, we need some number of tickets. So there are jobs and tickets. And some job requires some number of tickets. So for example, this one, only this one. This one requires these 3. This one requires these 2. We have to pay for some tickets, but then we can maybe execute these jobs that will give us some amount of money. Now, the problem is to choose which tickets to buy, then which jobs to execute, so that our profit is maximized. Of course, in the worst case, tickets are too expensive and we will not do any jobs. And in case all tickets cost 0, then we can just do all the jobs and get all the profit. Okay, so this is almost the network. So now we create a source and a sink. I'll think about the direction of edges. Yes, let's leave it as is. So we'll have all those infinite edges. We will draw edges to jobs with the cost corresponding to the money this job will give us. So A1, A2, A3, A4. And here we'll have this job, the ticket prices. T1, T2, 3, T4, and T5. Now, let's look at the minimum cut in this network. So the minimum cut might look like this. So we don't do these 2 jobs, but we buy these 3 tickets. So all the jobs in the same part as S. So we found ST to be the minimum cut. all the jobs and tickets that are in S, we will buy them and we will complete those jobs. And all these jobs that are in the right part, we will not do. So jobs, tickets in S, we will buy and complete. And in T, no. Well, let's see. So if we include a job in S, this means that all the corresponding tickets are also in S. If a job is in S, this means that all tickets, all required tickets, are also in S. Well, why? Well, because there is an infinite edge, right? So if we have S here, so if this is a job and it requires some tickets, these all are infinite edges. So these edges cannot cross the cut. So this means that these 3 tickets are also in the same part as this job. So the cost of this cut will include paying for all these tickets. So the mean cut cost is both tickets plus, so we pay for all the both tickets, so we pay for all the vertices that correspond to tickets but are in S. And we also pay for all the uncompleted jobs. So for all the jobs that are not completed, we will pay the cost of the corresponding edge from S to that job. So the cost of the minimum cut, or basically the cost of any cut, is both tickets plus non-completed jobs. And we would like to minimize that. So in the original problem, we would like to maximize completed jobs minus the tickets that we bought. Here, it's the opposite of that. So we minimize both tickets and minimize non-completed jobs. So we would like to minimize that. So we find the mean cut, and we just buy all these tickets, and we complete all these jobs that depend on those tickets, and we don't do these jobs. Basically, and the answer is sum of all A's. So basically, sum of all completed jobs minus the cost of the mean cut. Minus mean cut. And this will be equal to completed jobs minus bought tickets, which is exactly what we want. Okay, problem F. Any questions about problem E? Okay, so problem F. Let me read problem F. Okay, so we had some phrases or sentences that are either in one language, and we wanted to minimize the number that were, and each sentence is either in one language or in another, and we would like to minimize the number of words that are in both languages. So again, this sounds like a problem that can be solved with min-cut, right? So we need to divide words into two sets, and we need to somehow minimize the words that are in both sets, probably. This means that, again, instead of using a vertex for each word, we will use two copies of vertices for each word. So if two copies are in one set, then we will consider that that word is either in English or in French. And if cut crosses this edge, this will mean that this word is both in English and in French. So the trick here is, again, to split the vertices into two parts. And let's now try to create the network that corresponds to the result. Okay, so we have sentences. We have two entities, right? Sentences and words. And let's just split. Let's just create vertices for sentences and vertices for words. So sentences. And words. So, and as you remember, for each word we will have two vertices connected by a directed edge. So there is also sentence 0 and sentence 1, which we know that the first one is English and the second one is French. So we know that this one should belong to set S and this one should belong to set T in our min-cut. Okay, and we know that each sentence must be either in set S or set T. Okay, now let's have all these edges capacities 1, since we would like to minimize the number of words that are cut that have their two copies in different parts of the cut, which will mean that this edge will belong to the minimum cut and will contribute 1 to the answer. Now it's time to draw some infinite edges. Well, for each sentence, okay, let me look. Okay, so let's connect the sentence to each word in the sentence. So, for example, we have two words in the first sentence, this one and this one. We have some words in this sentence, and so on. As always, we'll direct incoming edges into the first copy of the vertex and direct outgoing edges out of the second copy. So we do it like this. So this is infinite. This is infinite. This is infinite. And so on. Well, all these are infinite. Okay, so now what does the path from 0 to 1 looks like? So from sentence 0, we go into some word. Then we go to some other sentence. Then we go into some other word. And maybe we go to sentence 1. Well, all the edges on this path are different. Are infinite, sorry, except for these edges that connect to different copies of one vertex. It's 1, and all the others are infinite. Well, if we find the maximum cut, the minimum cut, or the maximum flow, this means there is no path from 0 to 1. This means that for each path, there is at least one word, there is at least one edge that is completely saturated. Well, these infinite edges cannot be saturated. So either one of this word, or maybe two, maybe both of them, are cut. So now the problem is we need to cut some words. We need to cut some of those unit edges such that there is no path from 0 to 1. And this is a problem that is exactly solved with maximum flow or the minimum cut, right? So, and those edges that are cut will be edges that will be vertices that belong to both languages, right? So if this edge is cut, then the first part will belong to English, the set S, and the second part will belong to set T. And we need to cut the minimum number of such edges. This way we minimize the number of words, number of bilingual words in our dictionary. Okay, so this was a problem for some code gem. Yes? Sorry?
There is no path from 0 to 1.
This means there can be 0.
The source has to be on one side and the sink has to be on the other.
Yes?
But there are no edges.
Yes, there are no edges cut. If there is no path, then we don't need to cut any edges, and the answer is 0. So the mean cut is the mean number of bilingual words. So that was problem F. These were all problems on minimum cut, and now problems on minimum cost flow begin. I'll skip problems G and H, again, because they are just introductory problems, so you can test your implementation of the mean cost of our Hungarian algorithm. Okay, let's go with problem I. In problem I, you had jobs, and you had a machine that could do these jobs, but only if they are not intersecting. So the first machine can do this kind of jobs. The second machine could do these jobs. And the third machine will do this long job. Each job has a corresponding segment and the profit from this job. And we would like to find jobs for machines to do. I don't remember where we need to. Yes, and we need to tell which jobs to complete or not. Okay, so this looks like a problem where we need to split all the jobs, or split the maximum number of jobs into k different paths. So if we draw a graph, so there will be an edge from I to j if j can be completed after I. So in this case, there will be an edge from this vertex from this job to another job. This way, we need to decompose this graph into k paths where the total sum of all vertices is maximum possible. Find k paths. Of course, vertex disjoint, so each vertex can only belong to one path, such that the sum of vertices is maximized. Okay, so we'll do the same trick. Now we use mean cost flows instead of just flows because we have the cost to take each vertex or to push the flow along this edge. Again, we will make 2 copies of each vertex, and we will put capacity 1 and cost minus profit. Minus CI. So I1, I2. So for each vertex, we will create this edge with capacity 1. That means that we can execute this job just once. And with cost minus CI. Since we want to minimize the cost, if we put minus CI, we will maximize the total sum of vertices that we saturate using our flow. Okay, and there will be edge. If there is an edge from I to j, so there's j1, j2, we will put an edge with capacity, well, 1, doesn't matter, and cost 0. So if we can complete job I, then we just completed this job. Then we can skip some number of jobs, and then we can go to job j and complete it, and so on. And then we can go to t. Okay, so is this it? This looks like too many edges, right? So in this graph we had n equal to 1,000. So this will give us about 1 million divided by 2 edges, and even more. So this looks like a lot, right? So just finding one path is too slow. Okay, so what can we do? So we can make 2 types. Basically we can make 2 types of edges. We either complete this job, so we can move into any job after the completion of this. So if we complete this job I, we can only go to jobs that look like this. But what if we don't complete the job I? Then we can go to any job that intersects with it. So let's sort all jobs by the left border and make 2 types of edges. So if we complete job I, so we have I1 and I2. So if we complete job I, so 1 and minus CI, we can only jump to the next job after I is completed. Or if we go here, we can skip doing this job. That's fine. So we will go to the next job, so I plus 1. I plus 1. This has infinite capacity and 0 cost. So basically we have a list of jobs. We can either do this job and jump to the next job after this one is completed, and we get a profit for that. Or we can just skip the job and move to the next job in the list. This way we have the linear number of edges, since from each job we can jump to the next job after that one is completed. Or if we don't complete the job, then we can jump to the job number I plus 1. So now there is linear number of edges, and so n and the number of edges are on the order of 1000. So the total solution works in k times run the Ford-Bellman algorithm, and it's k times n times m. Usually it's faster, right? Usually the Bellman-Ford algorithm finds the shortest path faster than theoretical maximum n times m. Okay, that was problem I. The problem J was about, again, finding two vertex disjoint paths with the maximum cost, with the minimum cost. So we had a graph, and we wanted to find the path from A to C, A to B, sorry, that passes through C. And the shortest one. And the vertex is disjoint. So we cannot repeat vertices on this path here. Well, it's the same. Turns out if we move vertex B here, it's the same as we want to find two paths that don't have common vertices that go from A to C and from B to C. This can be modeled as again, as a mean cost problem. So we have S, we have T. We have this edge capacity 1 cost 0, capacity 1 cost 0. And we have this edge capacity 2 cost 0. Now we want to push 2 units of flow from S to T. Well, the number of vertices and the number of edges is very large, so we'll have to use potentials here. Initially, we can use potential function to be just 0. Yes, so we will run the Dexter's algorithm twice, right? First, to find the first unit of flow from S to T, then to find the second unit of flow from S to T, and we will update the potential function between those two runs, exactly as we discussed during the lecture. Okay, and to make these two paths vertex disjoint, again, we'll do this trick for the third time today, and make 2 copies of each vertex, and say that this has capacity 1 cost 0, and all other edges have capacity infinite and cost Ci, which is the length of that edge. And we need to find shortest path twice. So initially we set the potentials to be 0 since there are no negative edges. Then we find the shortest path twice. Then we update potentials as phi of u is distance from S to U. Then run the shortest path again. And we can use Dijkstra's algorithm since we have this potential function and we use it to make all edges non-negative. Any questions about problem J? Okay, so, and the last problem K. It's a hard problem if you don't know that you have to use Hungarian algorithm. Well, maybe not a hard one, since you have to match n objects with n objects. Here we had n points and n vectors, and we need to choose the matching between points and vectors, and we have to move corresponding points by corresponding vector, and such that the distance between any two pair of points will not decrease, and among those we need to maximize the sum of squares of all pairwise distances. Well, let's see. So we have point pi and we have vectors vi. So let's find the total sum of distances between all possible points. Well, what is a square distance? So what's distance between pi plus vi and pj plus vj squared? What is the distance? Well, the distance is a scalar product of the difference on itself. So it's pi minus pj plus vi minus vj on itself. Squared. Sorry, without square. So if we sum over all i's and j's, then we get this. Sum over all i's and j's of this thing. Okay, so we know that the scalar product is bilinear, so it's linear on its first argument and on the second argument. So this will be the sum over all i's and j's. I don't want to have all these 16 terms here. Oh well. So let's choose a permutation P that makes the correspondence, right? So here this will be pi plus v of pi and j v of pj. Let's change it a little bit. pi, pj, pi, pj. So there are 16 terms if I expand this scalar product, but a lot of them will be since we sum over all i's and j's. So for example, sum of pi times pi is constant. Sum of scalar products of pi and minus v of pj is also constant. Right? Since we sum over all i's independently and sum over all j's independently, this will be the same as sum of all pi's multiplied by sum minus sum of all vi's. The only non-constant terms that depend on this permutation pi is, so let me just write const plus, well, there will be pi times v of pi plus v of pi I pi plus, sorry, minus pj minus v pj, and the other way around. Minus v of pi j minus pi j. Okay, and these are all pretty much the same. So it's 4 times n times the sum over all possible i's, pi times the v of pi I. Again, plus some constant that does not depend on the choice of permutation pi. Okay? Everything else does not depend on pi. Independent of pi. So we need to maximize this. And how do we maximize this? Const plus 4n times this sum. Well, these 4 terms are the same. Right? So this can be made plus 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 plus. We can change the order, and since we are summing over all the i's and j's, this will just become 4n times the same sum. Okay, so let's create matrix Aij is equal to Pi and Vj, the scalar product of ith point and j's vector, and find maximum weighted matching. We can use Hungarian algorithm that definitely solves the problem, and depending on your implementation of the min cost algorithm, you might have success with this or not. So if your implementation is fast enough, you can squeeze it into the time limit, but the Hungarian algorithm definitely works. Okay, so there was one more part in this problem, is that the distance between every pair of points will not decrease. Well, turns out if the distance between a pair of points decreases, we can swap them, and the total sum that looks like this will increase. So basically, if the distance between these 2 points is less than the distance between Pi and Pj, we can change the matching, and the total sum of distances will increase, which will contradict with the fact that we found the maximum weighted matching. Okay, now, well, it works in n cube. N is 500. So the min cost algorithm will struggle, while the Hungarian algorithm should pass with no problems. Okay, so that's it. We're right on time. And do you have any questions? Okay, so again, if you have any questions in private, you can ask me. And
Yeah.